So now we will try to think about the following question. Why do we study eigenvalue problems? Right? I mean, given an n by n matrix, why do we even want to find its eigenvalues and eigenvectors? Well, we're not going to be able to answer this completely, but let's recall the following statement. If you have an n by n matrix A, and U1 through UK, say U1 through UK are eigenvectors of A with distinct eigenvalues, then the point is that these vectors, they are linearly independent. Okay. And as you recall, being linearly independent is one required property for being a basis. So what we have secretly been hoping for is that maybe we can find a basis consisting entirely of eigenvectors of A. And well, so what we're going to need to do now is to formalize this. The key is going to be the following definition. And we'll first of all formulate the definition and discuss at some point explaining why this is related to what we're saying about bases consisting of eigenvectors. Okay, so here's the definition. Suppose you have n by n matrices A and B matrices. Okay, A and B are similar. Similar. Okay, so the concept being defined here is similar if there exists an invertible matrix S such that B is S inverse A S. Okay, so we have two n by n matrices A and B. We say that they are similar to each other if you can write B, say you can write one of them as in terms of the other in the following form. Say B is equal to S inverse AS. Okay. Okay, so this is the definition. And the immediate remark, not remark, it should be a theorem. That if, suppose A and B are similar, say B is equal to S inverse AS, then A and B have the same characteristic polynomial, hence the same eigenvalues with multiplicities, with algebraic multiplicities. Okay, right? We know that if they have the same characteristic polynomial, they have the same eigenvalues with the same algebraic multiplicities. So the real thing to prove is that they have the same characteristic polynomial. Let's prove that. Well, by definition, the characteristic polynomial for B is the determinant of B minus Gi. And we know what B is. B is written as S inverse AS minus DI here. So that's that. Now, here's the trick we're gonna use. Well, the identity matrix here is the product of S inverse with S, right? That's the notion. That's the definition of the inverse, right? S inverse times S is the identity, so I can write I as S inverse S. But now, what I can do is I can factor this out. I can rewrite the term inside the determinant as follows. Okay, I can do determinant of S inverse A minus T, well, that's an I, S. Okay, that's just factoring the expression. So now you remember a property about determinant. That is, if you have a product of two matrices, the determinant of the product is the product of the determinants. So that means in this case, we are looking at, the determinant of S inverse times the determinant of A minus Ti times the determinant of S. Okay, and we like what we're looking at because what's in the middle here, this is the characteristic polynomial for A. So what we need is to show that there's nothing else. So we can rearrange these product, look at determinant of S inverse and determinant of S, determinant of A minus Ti, minus Ti, right? Then we can do it again. Determinant of the product of the determinants is the determinant of the product, right? Like that. And S inverse S is the identity. So you're looking at determinant of the identity, which is 1. This is 1. So you are left with the determinant of A minus Ti, which is the characteristic polynomial of A. So you start out with the characteristic polynomial of B and ended up getting the characteristic polynomial of A. So that's simple. Okay. Now warning. No, sorry, maybe not warning. Remark. If A and B have the same characteristic polynomial it is not necessarily the case that A and B are similar, right? The theorem above says that if A and B are similar, then they have the same characteristic polynomial, but the converse is not true. If A and B have the same characteristic polynomial, we can't conclude that A and B are similar. For example, if you take A to be this upper triangular matrix, a lower triangular matrix, this B is the diagonal matrix, right? Then both the determinant of A minus Ti and the determinant of B minus Ti is the same. It's 1 minus T squared, right? That's automatic. Not automatic, that's pretty easy to see. But I claim, there is, but A and B are not similar. B are not similar. Suppose they were. If there is S such that B is equal to S inverse AS, then what? You see, B is the identity matrix. The identity matrix is equal to S inverse AS, is what we're getting. Then now if you multiply on the left, multiply by S from the left, and multiply by T, so S inverse from the right. So let's do this in 2 steps. Let's multiply from the left by S. And then the left-hand side will become SI. That's, oops. SI is just S. Now the right-hand side is the following. You can combine these two. You can multiply these two first. That's S inverse, which is I. So you're left with AS. Okay. Now multiply by S inverse from the right. You get SS inverse equal to AS inverse. Now SS inverse is again identity. Now on the right hand side, you also have SS inverse, which is the identity. So you get I equals A. But A is not identity, right? So this argument shows that if B is equal to S inverse AS, and B is equal to A, because B is identity. But B is not A, so therefore B is not possible that B is S inverse AS. So A and B are not similar. Okay. All right. That's one remark. Here's another remark. Now, similar matrices do not necessarily have the same eigenvectors. Similar matrices do not necessarily have the same eigenvectors. We've just shown that they have the same eigenvalues, but the corresponding eigenvectors don't have to be the same. So for more precisely, we can see this as follows. So let's say that A and B be two similar matrices. Say B is equal to S inverse AS, and let lambda be the common eigenvalue with x not equal to 0 an eigenvector for B, namely bx is lambda x. Okay. Then what are we looking at? Now B equals to S inverse AS implies that if you multiply by S from the left, you get SB equal to AS. Then SBX is equal to ASX, right? Okay. So what? So now let's process this from two sides. The right-hand side, we process it as A times the vector SX. The left-hand side, we treat it as SBX. Now BX is lambda X, so this is S lambda X. So that's lambda SX. So what we get is A SX is lambda SX. So SX is an eigenvector for A, right? And of course, SX need not equal to X, right? S is not, in general, there's no reason for SX to equal to X. So even though A and B being similar imply that they have the same eigenvalues, for the common eigenvalue, they don't have to have the same eigenvectors. Okay. Now, next remark. Now, suppose A and B are similar. Matrices. Say B is S inverse AS. And then what happens? Then if I want to compute the case power of B, for some reason, here's what we can do. We can, B is S inverse AS, so it's the case power of S inverse AS. So you just have K copies of S inverse AS multiplied together. Right, so now here's the point. You see that the product always has this feature that there's in between there's an S next to an S inverse, and those pair will always get canceled. And likewise, there's an S with an X inverse not shown here that cancels. And this S inverse comes with an S that's not shown here, so it's canceled. So what happens is that the product here can be simplified to S inverse A. Well, how many copies of A? K copies of A. S. So B to the K, so or A to the K and B to the K are also similar. Right? And also, if, say, A is invertible, then B is also invertible, with B inverse being this expression. Right? We know B is S inverse AS. B inverse, if existed, is the inverse of S inverse AS. So according to the property of inverses, it's that. So the fact that this expression here makes sense shows that B is invertible, and this is the inverse of B. And secondly, this equality here tells you that A inverse and B inverse are also similar. Okay. Well, so now we come to the next important definition. Let's say A is an n by n matrix. A is diagonalizable if it is similar to a diagonal matrix. Okay. And certainly diagonal matrices are somewhat special, and we say that if a matrix is similar to a diagonal one, we call it diagonalizable. Okay. And the following theorem is as much as we're going to say about finding eigenvectors, finding a basis consisting of eigenvectors. Okay, so and that's the following theorem. So suppose A is n by n matrix. Again, A is diagonalizable if and only if there is a set of n linearly independent eigenvectors of A. Okay. And because we're working on n-dimensional spaces on N or Cn, having n linear independent eigenvectors means that these vectors form a basis. So this is our as much as we're going to say about what we're going to use eigenvectors for. Namely, we're going to we ultimately would like eigenvectors to form a basis, but that only happens when A is diagonalizable. Okay, now let's prove this theorem. So our assumption is that A is diagonalizable. So A is diagonalizable. say it is equal to, well, it's supposed to be similar to a diagonal matrix, ds inverse as with d diagonal and s invertible. Okay, right? This is the same. This. Having this equality with d diagonal and s invertible is the same as the following equation: as equal to sd with d still diagonal and s invertible. Okay. Now, s invertible here, this is equivalent to, as we talked about before, this is equivalent to s being non-singular, right? Now, if this is also equivalent to the following statement, if I write my s in column forms u1, u2, un with these guys columns, then being non-singular means that the columns are linearly independent. Right? Again, something we talked about before. Okay, now we need to further look at this equation. Let's see. Let's say D is diagonal, so let's say D is equal to, well, it's a diagonal matrix, so it's gonna look like this, with diagonal entries, say lambda 1 through lambda n, and 0 everywhere else. Now, we're gonna rewrite this equation, as equals sd, using the description that s is assembled by its columns. So that is going to look like AU1, U2, UN equal to U1, U2, UN times this D, lambda 1, lambda 2, lambda n, 0, 0. Okay, so AS equaling SD is the same as this equation. Now what do we know? Now we can sort of decouple this. Right, this is an equation of matrices. We can view this as n equations of column vectors. A times the matrix u1 through un is the matrix given by columns AU1, AU2 down to AUN, and these are columns. Now, B here, not B, on the other side, if you work out how the matrix multiplication works, in this case, you see that the matrix with columns U1 through UN times this diagonal matrix D is just multiplying, it's just the matrix given by multiplying the column U1 by lambda 1, column U2 by lambda 2, and so on, like that. And still, U1 through UN are linearly independent. Okay, but this is exactly saying that each of the U's is an eigenvector, i.e. U1 through UN are n linearly independent eigenvectors. Of A. Okay, so that's simple as that, right? Okay, so now looking at this theorem, we know exactly, or rather looking at this, the proof of this theorem, we know exactly how we want to try to diagonalize a matrix, right? We need the column, we need the eigenvectors. Let's look at this equation. We need the we need the U's or the columns of our matrix S to be the eigenvectors, and for the diagonal matrix, the diagonal entries are going to be the eigenvalues. Okay, so what we need is to be able to find n linearly independent eigenvectors. Then we can form this. There's an immediate corollary that we should formulate before we move on to examples. If A, again n by n, has n distinct eigenvalues, then A is diagonalizable. Right? This is because the proof, quickly, we've seen already that eigenvectors with distinct eigenvalues are linearly independent. And because we have n distinct eigenvalues, we have n such eigenvectors, and they are linearly independent. So according to the theorem above, our matrix A is diagonalizable. Okay, so this is a generality, and this you can then view the purpose of studying eigenvalue problems as deciding whether a matrix A is diagonalizable or not. Let's look at some example. I'll do a simple one. A is a 2 by 2 matrix, 5, 3, minus 6, minus 4. And we're going to try to diagonalize it, or ask the question diagonalizable. Okay. Well, so what do? We have to decide, well, the problem is now first solving the eigenvalue problem first. Okay, so we have to compute the eigenvalues and find the eigenvectors and so on. Okay, so the characteristic polynomial is the first thing to compute. And that's not quite the end of it. Have to simplify. T squared T squared what? Minus 4 and minus 5 plus 4 minus 1 plus, well, not plus, minus 20 plus 18 minus 2. Okay, so this is t minus 2 and t plus 1. Yeah. So the eigenvalues are 2 and minus 1. And because A is a 2 by 2 matrix, and it has 2 distinct eigenvalues, so we know it's diagonalizable. By the corollary above, but we want to be a bit more detailed, actually compute the diagonalization. So for that, we have to solve for the eigenvectors. So in this, let's say let's do the lambda equals to 2 first. We need the system ax equal 2x or a minus 2I, x equals to 0, which is, what is the system? So 5 minus 2, 3, 3 minus 6 minus 6, x1, x2 equal to 0. Well, it's only, as you can see, the two equations are the same. It's really just x1 equals to x2, right? So the eigenvectors are 2x2, x2, so x2 times the vector 2, 1. So these are the eigenvectors. In particular, you can take, you just need one vector. You just need one eigenvector for the purpose of diagonalization. So you can take U1, say, to be 2, 1. Now for lambda equal to minus 1, we are looking at the system AX equals to minus 1x, or A plus I x equal to 0, which is the same as 6, 3 minus 6 minus 3. X1, x2 equaling 0, 0. And you can immediately see that this equation is, these two equations are the same. It's x1 equals x2. So therefore the eigenvectors are multiples of 1, 1. And once again, we can take one of them, say U2, to be 1, 1. And now going back to this equation that we had earlier, this one, I mean, the diagonalization is going to come from this. Right? What we have to do is to use the eigenvectors of our choice to form a matrix S, and the diagonal entries. Well, the diagonal matrix will have its entries being the eigenvalues. Okay, so we can do that. So we then have A, well, U1, U2 equal to U1, U2 times lambda 1, lambda 2. Lambda 1 is 2, and lambda 2 is 1 minus 1. Okay. And more precisely, U1, U2, the matrix formed by U1, U2 is 2, 1, 1, 1, like that. 2, 1, 1, 1, 2, 0, 0, minus 1. Okay. All right. So there's just one more thing to do. Let's call this guy S. And we need to compute S inverse. This isn't too bad because it's a 2 by 2 example, so we can basically read it off like that. And now what this is saying is that 1 minus 1 minus 1, 2, A, this is S inverse, right? And then S, 2, 1, 1, 1, this is equal to the diagonal matrix 2, 0, 0, minus 1. Okay. Now suppose I want to compute a power of A. So let's call this guy D for the moment, just so that we can simplify the discussion. So in this notation, A is equal to S, D, S inverse, right? So the 100th power of A is SD S inverse raised to 100th power. And we've done this a little while ago. That is, if you just write out the full multiplication, you're seeing that there's in the middle of it, this product S inverse is accompanied by S always. And those things canceled. What's left in the middle is the 100 copies of D. So you end up getting this expression. Now, this is simple to compute now. Because first we know what S and S inverse are. S is this. D is this guy. Now, if you multiply D 100 times, what happens is you just multiplying the diagonal entries 100 times. So you end up getting A to the 100th power to be this, and this is not very difficult to expand. We will not do it. But this is a point worth making, that in general, if A is diagonalizable, say D is S inverse A S, then you can check by the same argument that the case power of D is the same as S inverse A, the case power, S. So if you are to compute the case power of A, you can do it from here. That's SD to the case power, S inverse. And D to the case power is easy to compute. Right, so this is an example of, well, this is at least one use of diagonalization. If you are to compute a power of a matrix, that makes it simple. If you diagonalize it first and compute it on the diagonal matrix. Okay, and let's see. So let's do one more example about diagonalization. Say A is 1, 1 minus 1, 1. So again, the question is if it's diagonalizable. And for this, we will need to solve the eigenvalue problem. And the first step is always the computation of the characteristic polynomial, which turns out to be t squared minus 2t plus 2. Okay. And what this means is that the roots are okay, and by the quadratic formula, minus 4ac, so 4, yeah. So what is this? This is inside is minus 4, so it's 2i after the square root. So it's 1 plus minus I. And this tells us that the eigenvalues are 1 plus minus I. Well, complex numbers, but still distinct. So we know it's diagonalizable. Very good. But we should still try to find the eigenvectors if we are to complete the diagonalization process. So for the eigenvalue 1 plus I, we need ax equal to 1 plus ix. So that's the same as minus I minus 1, 1 minus I, x1, x2 equal to 0, 0. And you can see here that well, this is the same equation. These two equations are again the same because they differ. The two rows differ by a factor of minus I. So you're just getting that x2, x2 is ix1. So, right. Hold on. Yeah, x2 is ix1. So the eigenvector x1, x2 are just ix1. No. x1, ix1. So x1, 1i. These are the eigenvectors. And we are supposed to pick one of them. So take u to be 1i. Now for the other eigenvalue, we proceed similarly. That is, well, let's see, I minus 1, 1, I, which you see again, the two rows again differ by a factor. This time the factor is I. So you really have, again, the same equation, but you just have one equation. This time the equation is x1 equal to ix2. So the eigenvectors are ix2, x2, x2, I1, and you can once again take one of them. So for example, I1. And then you are now ready to assemble 1 minus 1, 1, 1. Say U1 here, U2 there. Then this is going to be U1, U2. What? Well, the two eigenvalues being on the diagonal and 0 elsewhere, right? And again, this is supposed to be S. Right. And S is, to be more precise, 1I, I1. Or not. Well, doesn't, I guess it's okay to be that. Yeah, no, that's fine. Yeah. Okay, and 1I, I1, 1 plus I, 0, 0, 1 minus I. So I guess to be complete, we still have to compute S inverse. Again, this is a 2 by 2 example, so S inverse is easy to compute. It's 1 over the determinant. The determinant is 2. And you interchange the terms like that. And we can check that this is indeed the case. Yeah, that's correct. Okay, so with this, now we've completed the diagonalization process. Okay, so now it remains to talk about the special case. There's a special case of matrices that we are guaranteed to be able to diagonalize. That's the topic of next lecture.